Hi everybody, Dr. Pingle here. We are going to work through an example of pole photogrammetry. This is a data set that was collected by students Ivy and Zach on the campus with a GoPro Hero 11 mounted on a short pole. They took, we can just measure here, 250 images, each at about a second apart. And this is a pretty nice data set. You can sort of see a lot of detail in this tree. It looks like it's maybe right outside Old Johnson. So if you look at the whole span of it, you can see that some of these are going to be able to get the trunk. They really kind of vary around. So it's a nice data set. So to get started with this, we're going to create a new data set. So I've actually run this as kind of a test for this video. So we're just going to call this Ivy and Zach, and I think I saw Robert in that image as well. And we're just going to add all of these images in. So Control A to add them, and then drop them straight in. If we hit Next, we'll start looking at that camera model. We'll pull these coordinate systems and we can start to take a look at it. Now, in a lot of videos, we might pay some pretty close attention to these coordinate systems, and in fact, I suppose we may as well. We know that this is coming from a GPS, and GPSs don't typically give us orthometric height; they give us an ellipsoidal height. To get to that menu, you'll want to make sure that the advanced coordinate options is on. So we'll hit OK there. All of these images are geolocated. Horizontal accuracy and vertical accuracies aren't individually flagged. So they're globally flagged here at 5 meters and 10 meters. That's probably overly pessimistic, but it doesn't really matter. The catch to getting this all to work, with a GoPro camera in particular, is to make sure that the camera model is specified correctly. So if I hit edit on the camera model that I have, likely yours will come up if you run this as a Hero 11 Black. That should be in the metadata. It's a 20 megapixel camera or so. The problem is that most, here I'll hit cancel here, most camera models for the Hero Black are going to look something like this. Now the problem with this is a perspective lens, but the GoPro is clearly a fisheye lens. If you look at these images, the fish-eye-ness of it is pretty clear. Straight lines, these are straight line sidewalks, and you can see how bent they are in this image. That's a good indication. When straight lines aren't straight, that's a good indication that you're not working with a perspective lens camera. So the mechanics of this are a little bit more detailed than I really want to get into, but the gist of it is that you can model a fisheye lens with a perspective lens if you get all of these things right. But it's actually just easier to use a good camera model. And so this is a camera model that I will post along with the tutorial. I'm using a fisheye lens. It's set to a global shutter, even though that's not technically true on a GoPro. It's not capturing all pixels at exactly the same time. There is what's called a readout time. And so you could use a linear rolling shutter, but you generally only want to do that when you're doing sort of like grid sampling from a drone. It just doesn't really work very well on the ground. And the readout time is fast enough that it'll be fine. Sensor width, height, and pixel size are all determined from the specs of the camera itself. So GoPro used to publish these pretty regularly. I think they've sort of stopped publishing these, but these are reasonably good guesses about those. And then the principal point is usually approximately half of the sensor width, and then this principal point is half of the sensor height. So most of this stuff is pretty well determined. Now the polynomial coefficients and the affine transformation numbers, those you kind of have to get from at least one successful run. And a good way to do this is to fly your camera on a drone with GCPs and then do the reconstruction that way. And in that way, you will come up with a good camera model. So that's what I've done here. These estimates are all from a good quality drone flight, and they're not perfect, but they're pretty close. And in fact, temperature differences and light differences can change what these camera models are like. So, you'll essentially create a new camera model off of the Hero 11 Black, and you can fill in these numbers. You can fill in those numbers as well. You don't have to get them right to the last decimal point. If you get these to the third decimal point, that's close enough, because it's going to be modifying these anyway. So we'll hit cancel here, and we'll hit next. The output is known. You'll probably want to make sure that this is actually set to the EGM96 ellipsoid. Now, this is a pretty small model, so there's a good chance that we aren't going to be able to get this upright anyway. So the necessity of trying to get all of this stuff inside of an actual coordinate system is not that strong. But in fact, if we wanted to spit these out in what would be called an arbitrary coordinate system, we could do that. Just get rid of our geospatial information entirely and do it that way. But we'll leave this alone for now. So auto detected, we'll go ahead and leave it at EGM96 and just hit next. We don't have any GCPs here, and the camera that we're using here does have a GPS, but it's not a RTK GPS. In fact, it's quite inaccurate. We're going to use the 3D models to do the reconstruction. Now, the difference between models and maps, both are 3D, so we are generating point clouds and digital surface models as well as orthomosaics with the 3D maps. But with 3D models, we're sort of envisioning a site that's either a statue or a single building. Things like that are a little bit more appropriate for models. Things you wouldn't really want to try to generate an orthophoto from, I suppose. So we'll choose models and we'll hit finish. Now, you'll see that by default, 3D models only enables the first 2 points, and that's good. You're also noticing, hopefully, that as they walked around this tree, you can sort of see the rings. The GPS signature isn't perfect, but the general location here is pretty good, just sort of an area right outside of Johnson Home. Now, the settings for this are generally not so good, so we're going to need to make some minor modifications here under initial processing. Probably best to leave this at full. It's often a good idea to turn on this geometrically verified matching, and it's often a good idea to turn on rematching as well. So those are the 2 settings that I would change under initial processing. And if you don't have those, there's a little checkbox here for advanced that will let you turn those on. For point cloud and mesh, I always like to export an LAZ rather than an LAS. They're smaller. Not that this one is going to be terribly large. The LAS is nice in some ways because it's directly compatible with ArcGIS Pro, but you can always do the conversion. I always like to merge these tiles into one. Again, this is a pretty small reconstruction, so I don't necessarily even think that there would be more than one tile, but just in case, it's nice to have that checked. The 3D textured mesh is on. We're going to go ahead and generate that and look at it. OBJ is a pretty fine format. You could turn on PLY if you want. I usually don't bother to turn off FBX, but you could if you wanted to. Most of these you can kind of leave alone. And then you almost always, again, on any Pix4D run, want to just bump this down a little bit so that you're not swamping your computer. So we'll hit OK here, and then we would go ahead and start the run. So I could hit start. Now I happen to have finished this run, and so we can just go ahead and take a look at those results. The whole reconstruction of this took, I didn't measure it, but something in the order of an hour or 2 on my computer, which is a very strong computer that was built about 6 or 7 years ago. So kind of a good to medium computer now. So this is the kind of thing that is going to tax some resources for sure. I did move these images. If you do that in Pix4D, it's actually pretty easy to find them again. So we can just point them back to that image folder here, and it will reassociate those just fine. Okay, so to take a look at the output, we can take a look at the ray cloud here. Now, as I've generated all of this, one of the things that you'll notice is that we're getting a lot of this surrounding area that's actually not necessary. And so I'll point out that there's kind of a nice feature in Pix4D, which is that you can define the processing area. So you can click around and then right-click to finish. 1, 2, 3, 4, 5, 6, 7, doesn't really matter, 8, and get an area that looks like this. And what this is going to do, in fact, I may show this at the end of the clip here. What this is going to do is prevent all of this extra stuff from happening, all of this junk that we're getting kind of at the outside. These are all buildings, there's part of a reconstruction in here, but they're at such an odd angle that they're really not a very high quality. If you zoom in, you can see the street network pretty well. In a structure from motion reconstruction, there are a lot of random points that get generated. So this kind of noise in the data is not so unusual. You can totally denoise an image. And we can see that the blue are the original GPS points and the green are where I thought it was. This is a pretty reasonable reconstruction. It looks about like someone pointing a camera at a tree and walking around it. So I think that this has done a pretty good job. You can click on point clouds and you can get rid of the tie points and rays in cameras, and in this way start to get a sense of the reconstruction of that tree. So we've done a pretty good job here with the fence. So a lot of good detail on that. And then the tree itself is pretty good. Now, the representation of this point cloud is a little bit unique to Pix4D, and so let's take a quick look at what that would look like on the inside. So here's the folder for that run. I'm going to click inside of the densification, and here I have the 3D mesh that was made in the point cloud, and we can take a look at both of these. In fact, we haven't looked at the meshes in Pix4D, but we could do that as well and turn off point clouds and point groups. Don't care about that. There we go. And so this looks a little bit more realistic. A lot of the details in between have been filled in, so it looks pretty good. But wherever there's an error, you get these sort of like bubbly surfaces. So around the chain, it's a pretty tough reconstruction to do. So it's a complex surface, and the post looks a little bit weird. Now, there was a higher resolution setting that we could have done to try to improve this a little bit. So this is far from the best that one can do with this, but a pretty good example. So the point cloud is here. So these we'll talk a little bit more about point clouds as we get into the LiDAR section. But an LAZ file is a compressed version of an LAS file, which is a point cloud file. We're opening it up here. We've got all of these different attributes we don't actually need. We could maybe keep intensity, I suppose, if we wanted to here. These kinds of shifts, you can just hit OK. I'm using a software called Cloud Compare, which we're going to be getting into in some detail. And now that's loaded the point cloud, and now we can see that tree in a little bit more detail, both what it did get and kind of what it didn't get. When you're doing a reconstruction, not every point in the environment is going to come back. Basically, what it needs to do is find a common point in several photographs to be able to say, yes, that's a feature. And so if you're in areas that aren't all that well differentiated, it can be a little bit difficult to do that. A lot of the stuff around here is sort of outside the zone of where the data was really kind of collected, so it's not surprising that the car is kind of barely filled in here. You can tell that this is a sign, but you can't really read it. But as far as the tree goes, we've got a lot of branches and leaves, but it's actually quite a complex surface, and so trees are exceptionally difficult to reconstruct with standard methods. I do encourage people to play around with other ways of doing this. Luma AI is kind of my favorite way to construct what are called NeRFs, or neural radiance fields. We'll probably talk about those at some point, but this image set would probably work quite well with that. And then things like the chain, we'll see if we can get in here. Things like this chain actually get represented reasonably well. Individual links are sort of visible. There's a little bit of noise in here, but overall this reconstruction is quite good. And even something as simple as like measuring tree diameter, is very easy to do. This tool set has some really nice ways to start to slice your data. So if you didn't sort of define a study area in Pix4D, you can do a lot of those kinds of things here. There's kind of a smaller little bit of it here. And then what I wanted to show is just, you can take little slices. If we wanted to look at, just say that, just a little bit of the trunk of that tree. You can do that as well. I came up just a little bit too high on it before. Yeah. So here's just a ring of the outside of that tree. We can take measurements of that if we wanted to. Something like that. Now, the measurements of this are actually not quite right, I'll point out. And part of the reason for that is if we go back into Pix4D, the GPS is being operated over such a small area that the distances between all of these individual little points have a lot of error associated with them. So it actually has a hard time figuring out which way is up, and it has a hard time figuring out what the exact distance is between these points. There are ways to fix that. That's a little beyond the scope of this little video. So really this is about taking a couple hundred photos and turning them into a nice 3D model. Both sort of the advantages of a model like that and the disadvantages. Lots of information in the point cloud, although not everything. Lots of information in the mesh as well, which, by the way, you can just load using sort of common Windows mesh viewers, but also sort of it's a little bit tougher to sort of get the full reconstruction as you would think it should be. All right, we'll wrap it up there. Thanks, everybody. Thanks for Ivy and Zach and Robert and anybody else that was a part of this data collection. Good work.